So this is your warm up for today. If you have not done it yet, please pause the video and get this done before you check the answers. This is from section 6.1 that you guys did. So if you have two different linear functions, f of x and g of x, part A you're adding, part B you're multiplying, part C, remember you're putting, this is called composition of functions, where you're putting g of x inside of f of x, and this one's going the other way. You're putting f of x inside of g of x, and then on this one, you are evaluating g of -1 and then taking that answer and evaluating f of -1. That's one way you can do that. So pause it before you go on. So here are the answers. And on part C and D, I did show the work that I did. Actually, notice how I did part E, what you can do, since you just solved f of g of x in part C, and you got 6x plus 1, well, now you can just take the -1 and plug it in where the x is and do 6 times -1 plus 1, and we get -5. So that's just a little recap of what you guys did in the last section. So today we're going to talk about inverse functions and relations. And your learning targets, what you should come away with knowing is I can find the inverse of a function or relation, and I can determine whether two functions or relations are inverses. So we're going to learn what that means and apply that. So first of all, a little definition, vocabulary. A relation is just a set of ordered pairs. So for my first example, I have the set 5, 2, and 3, 0, 2, -3 as ordered pairs. Remember, in your ordered pairs, we have the x coordinate and the y coordinate. The x coordinates make up the domain. So like for this particular relation, the domain would be 5, 3, and 2, and the range are the y values, would be 2, 0, and -3. And sometimes you'll see these listed in order from least to greatest. Now the inverse relation is just the set of ordered pairs that you get when you reverse the coordinates. So instead of 5, 2, you write 2, 5. Instead of 3, 0, 0, 3. Instead of 2, -3, -3, 2. So notice for my inverse relation, my domain is now 2, 0, -3, and my range is now 5, 3, 2. So notice that my domain and range swapped places when I compare my relation to the inverse relation. So what I'm asking you to do here is we're going to graph two linear equations. You should be really good at graphing lines. So assuming that I am counting by ones on my x and y axes, I want to graph y equals 2x plus 4. So I'm going to use, since it's in slope-intercept form, I'm going to use the y-intercept of 4. My slope is 2, so I'm going to go up 2 and to the right 1. Or you could go down 2 and to the left 1. And then we'll draw in our line. Then for my other graph, my y-intercept is -2, and my slope is 1/2. So I'm going to go up 1 over 2, up 1 over 2, or down 1 to the left 2. And I'm going to draw that in. So we're going to talk, I don't know if you notice on this, there is a relationship between these two lines. If you compare them, I'm going to draw in the line y equals x. This is our identity line. So if I draw this line in, and I'll label this y equals x, I want you to notice that these two lines that I have in blue and red, they actually look like a mirror image. If I could fold this on my dashed line y equals x, they would fold onto each other. So we say that these two lines, they're symmetrical. across the line y equals x. And we're going to talk about a special relationship between these two lines that makes this true, where they'll be symmetrical across the line y equals x. So we'll come back to this picture in a minute. This was the one that I graphed in blue, y equals 2x plus 4. So I want you to think about what operations would you use if you had to solve for x. So if you were undoing this and trying to get the x by itself, well, the first thing you would have to do would be subtract 4. So we'd have to do that first because we have to unbury the x. And then the next thing you would do is divide by 2. Okay, so let's suppose that I start with an x and I subtract 4. So x minus 4. And now I'm going to divide the whole thing by 2. Well, I could split this apart and say that's 1/2 x minus 4 over 2. Or I could just call this 1/2 x minus 2. So now if you look back at my second equation, it was 1/2 x minus 2. And what I just showed, when these were the operations to undo something, this is showing that these two equations are inverse functions, because one of them you can get from undoing the steps, which makes them inverse functions. When you have inverse functions, they are symmetrical across the line y equals x. So I'm going to write inverse functions are symmetrical across the line y equals x. So that's one way that we can kind of think about what an inverse would be to a function. We can think about what steps would I do to undo them. So we have a notation that we use for function notation. Instead of y equals, we use f of x equals. And we also have a symbol that we use for f inverse. And it looks like a -1. So it would, especially after we've just done exponents and we talked about how -1 means reciprocal, but not in this context. So when you see this written, f, and then you see that -1, you don't want to think of it as f to the -1 power. You want to read that as f inverse of x. So if f of x is 2x plus 4, we just saw that f inverse of x is equal to 1/2 x minus 2. So those are inverse functions. So suppose f and f inverse are inverse functions. This is kind of a mathy sounding definition. It says then f of a equals b if and only if f inverse of b equals a. And really what this is saying is your inputs and your outputs swap places. Remember back at this very first example I showed you of these relations, how my domain, my x values, and my range values flip-flopped, or they swapped. Well, that's the same thing that would be happening here in this description. So if we know that f of x equals 2x plus 4, and f inverse of x is 1/2 x minus 3, and I want to find f of 3, then you know that we're going to substitute a 3 in, and I get 10. So to illustrate this, now let me find f inverse of 10. So if I take 1/2 times 10 minus 2, half of 10 is 5, minus 2 is 3, notice I got this value back. So that's what is illustrating right here. Now, this would not prove that these were inverses if I find one example that works. To prove it mathematically, I would have to show that every number that I plug in for x into f of x, I would have to show that for every single possible number, every decimal, every fraction. Well, there are infinite possibilities, so it's not possible to show that something is inverse, you can get a pretty good idea, but you can't prove it mathematically by just plugging in a number. We have to do something else algebraically to show that it's true as a mathematical proof. Here's another way to find inverses, and this is extremely helpful. Now, this is a different function right here, so I'm using a different function. So f of x equals negative 1/2 x plus 1. So we're going to follow these steps. The first step says replace f of x with y. So I'm going to call it y equals negative 1/2 x plus 1. Now interchange x and y. Okay, so I'm going to have x equals negative 1/2 y plus 1. Next, I solve for y. That means get y by itself. So I'm going to subtract 1 from both sides. So I get x minus 1 equals negative 1/2 y. And now I'm going to I want it to be just a y. So if I multiply this side by negative 2 over 1, notice the 2's cancel, the 1's cancel, the negatives cancel, make it positive. So I'll just get a y, which is what I want. But I also have to multiply this side by a negative 2 over, I don't need the 1. So I'm going to get negative 2 times x is negative 2x. Negative 2 times the negative 1 is a plus 1. And then the last step says replace y with f inverse of x. Well, I'm going to list this first. So f inverse x equals negative 2x plus 1. That means that this is an inverse to the negative 1/2 x plus 1. Remember what I said about the graphs of inverse functions. So I actually typed in y1, my first, the y1 equals negative 1/2 x plus 1, and I put what I got for my inverse in y2. So if I look at the graph of this, here's what I get. Now remember what I said about how it should be symmetric across the line y equals x. So let me add that line on there. And now you might look at that and say, well, I don't really see it perfectly symmetric if it went across that line. One of the reasons why is because if you look at my grid, it's a rectangle, so it's not really squared off. Look at the tick marks on the x-axis and the tick marks on the y-axis. You can kind of see that they're not the same. So if you go zoom, and number 5 is zoom square, that squares it off better. So it's a little easier to see that it is symmetric across the line y equals x. So that's a good way you can kind of get a visual to make sure that your inverse function is correct. So for this next one, I highly recommend you pause this and try answering the question. So find the inverse of each relation and then tell whether or not the inverse is a function. And if you forgot what to do on that, I'll remind you. But pause it and give this a try. So here are the answers. To find the inverse, you're just going to switch the x and y values. The first one is a function, the inverse is a function, and in part B, the inverse is not a function because in the inverse on part B, you have x values repeating. We have a 9 going to a negative 2 and a 9 going to a negative 7. Remember, to be a function, the x values cannot repeat. So in both situations, the original what I wrote were functions. The relations were functions. But in part B, the inverse is not of that relation is not a function. All right, so on this next one, the task says to find the inverse of the function and then graph the function and its inverse. Is the inverse a function? So I'm going to do this by with our method of, you have a couple ways. You can think about what to undo it, or follow the steps where I said change it to y equals negative 3x, swap the x and y, and then solve for y. So I'm going to divide by each side by negative 3. And I'm going to write this as y equals negative 1/3 times x. It's easier to get it like with the slope, which now I'm going to put it back into function notation. So here is my inverse function. So for the first one, this is like having plus 0. So my y-intercept is 0, 0. My slope is negative 3, so down 3 over 1, or you could go up 3 and to the left 1, and we get our graph. Okay, that's not a very good line. Should have got a line tool out. And for our other one, also 0, 0, and the slope is negative 1/3, so down 1 over 3, or we could go up 1 to the left 3. You want to make sure your line is going in a negative direction, and there is my inverse. Now you should label them. So this is f inverse of x, and this one is f of x. I know I had colors on there, but you usually won't have colors on there, so you should label them. Now notice how I drew my line in, my y equals x line. You could see that they do match up right. Okay, so find the so this is another one. So we're going to try this again. Actually, I'm going to pause this or I'm going to have you guys pause it, and I'm just going to work it out. But you guys pause it and try it. Okay, so I went through and found my inverse. Now notice I got to this point where I have x plus 6 all over 4, and I split it apart. So I had 1/4 x plus 6 over 4, which reduces to 3/2. So then I graphed both equations, I labeled them, and then the question, is the inverse a function? So my inverse is what I have drawn in blue, and notice it passes the vertical line test, if you remember that from earlier on in the course. So then my answer is yes, it would be a function. I don't know if I answered that one on here. Is the inverse a function? The answer would be yes. Look at my red line, it passes the vertical line test. So both of those examples, they were functions. So now we have another one. Find the inverse of the function and graph the function. So same directions. So on this one, I'm going to start by labeling this y equals x squared minus 3. So I'm going to have y plus 3. Oh, forgot to switch. So I'm going to have x equals y squared minus 3. I'm going to have x plus 3 equals y squared. And then I have to square root both sides. So when I do that, I'm going to flip-flop these. I'm going to get plus or minus the square root of x plus 3. So that's kind of complicated. You might not even know quite sure how to graph that. So I'm going to show you a different way. So we know what h of x looks like. X squared minus 3. It's a parabola. It's the parent graph down 3. So here's my negative 3. And since it has the shape of the parent graph, it's going to go over 1, up 1. And it's going to go over 2, up 4. And if I wanted to go over 3, I would go up 9. And I'm going to draw that in as carefully as I can. Kind of made that look not curved enough. Okay, now I want to come up with the inverse, but I'm not quite sure how to graph that. Well, I know how to graph it, but you don't. So we're going to do this another way. Let's think about the ordered pairs on here. So I know that this is 0, negative 3. I know that this is 1, negative 2. This is negative 1, negative 2. This is 2, 1. And this is negative 2, 1. I'm just going to try it with those. I'll do it in blue. So I'm going to swap the x and y values. So instead of negative 2, 1, I'm going to graph 1, negative 2. Instead of negative 1, negative 2, I'm going to graph negative 2, negative 1. Instead of 0, negative 3, I'm going to graph negative 3, 0. Instead of 1, negative 2, I'm going to graph negative 2, 1. And instead of 2, 1, I'm going to graph 1, 2. And I'm going to draw that in. Okay, notice I get a parabola that kind of looks like it's lying on its side. If I graphed the line y equals x, it would be symmetrical across that line y equals x. But this is not a function because what I have in blue, notice that it does not pass the vertical line test. So sometimes when you graph a function, if you're not quite sure how to graph the inverse, or maybe you can solve the inverse, but then you're not sure how to graph that with the plus or minus, if you use your calculator, you have to graph the positive square root of x plus 3, and then in y2 you would have to put the negative of that. But this works out really well, just to graph the function and then swap the values in the ordered pair. So this next, again, another relationship with inverses. Two functions, f and g, are inverses if and only if. When you see an if and only if statement, that means it goes both ways. Both of their compositions are the identity function. So that means if I put an x inside of g, and then I take that answer and put it inside of f, I should get what I started with. And that's the idea of an inverse function. So to find, and we did this, remember we did this in the last unit. So if I want to find f of g of x, that means I'm taking g of x and putting it inside of f of x. So when I do that, I get 2 times, I'm going to replace the x with 1/2 x minus 2, and then I have plus 4. So all I did was dropped the g of x in place of the x inside f of x. Distribute this 2. 2 times 1/2 is a whole, so I get just x minus 4 plus 4, which equals x. So that's good. Now let's go the other way. So if I take f of x and drop it inside of g of x, I'm going to get 1/2, replace the x with 2x plus 4, and then I have a minus 2. Distribute the 1/2, so 1/2 times 2 is just a whole, so I get x. 1/2 of 4 is 2, minus 2 is x. So that proves that that f of x and g of x are inverse functions. When you do the composition of functions both ways, and you get x. So on this one, for you to practice, you can pause this and try it, and I'll go through it to determine whether if these functions are inverse functions, justify your answer. So go ahead and pause it, please, and try it. Okay, so I'm going to try doing f of g of x. So I'm going to take g of x and drop it in here. So I get x plus 7 minus 7 equals x. That's good. Then I'm going to try g of f of x, which means I'm taking this and dropping it here. I get x minus 7 plus 7, which gives me x. Therefore, in math, that means therefore, f of x and g of x are inverse functions. Okay? And last one, maybe that's the last one. Oh, nope, guess there is another one. Go ahead and pause this and then I'll go through it. Okay, so on this one, I put g of x inside of f of x. And then I distributed this 1/2 times the 2x, I got x. 1/2 times negative 4/3, you'll get negative 2/3. I didn't even do the math. These are not going to cancel, so it's not x. So the answer is no. You don't have to test the other way, because if it doesn't work one way, the answer is no. This problem, just think about it. And we can prove it, but think about why f of x equals 2x cubed. We know that the shape of this graph is going to look something like this, because it's a cubic function. We've talked about cubic functions. Square root functions, we've talked about those as well a little bit. And so we are going to see something like this, like half of the parabola on its side. There's no way those can be inverse functions because you're not going to see it symmetrical. So the answer is going to be no. They have to be at least, similar types of functions in order to do that. So that's it. I know that was kind of a long video. Make sure you get your notes uploaded, please, and get working on your assignment.